not even in the middle. What? Have you tried? Did you see the message about the mask?
Yeah, sure. I'll just send you messages.
Okay. Yeah. Good. All right. So let's get started. So we're talking about batch IL, and so far offline RL. Maybe I will change. But so far we have mostly seen the case when the focus was not on generalization, that is using function approximation, but it's like if you don't have any approximation errors, what can you do? How far can you get? And we have seen that there are big differences between, like, regarding how the samples are generated. It's a coverage thing, right? Like if you have control over coverage, you'll be fine. In general, if you can only sample from policies, some trajectories, then in the worst case sense, this is already too hard. So we can bring in functional approximation. So far, people call this tabular, I don't know, like this name just stuck, but I think it's a horrible name, but, and people are also using it as a little bit of a belittling, like remark that, oh, it's just a tabular case. But I mean, that's almost everything is that. Anyways, so there is no generalization, no approximations. And the question arises, how does the situation change if you bring in approximations, if you bring in function approximation? Well, the very simplest case of function approximation when there is no function approximation, so things cannot get much better. But things can change in the sense that, like, maybe, like things are exponentially hard originally in the horizon and the size of the state space, and maybe in the case of policy sampling, and okay, maybe the size of the state space shouldn't show if you are doing state abstractions, right? At least in the bounds. So that's something that one expects. Also, so just replacing states with the number of features, if you are using linear function approximation everywhere in the bounds, or maybe if you are doing feature extraction over state action pairs, then replace the number of state action pairs with the in the bounds. This is sort of what you expect. And the question is, can we really do this, especially when the functional approximation is not perfect? If the functional approximation is perfect, in one sense, there are many ways in which, I mean, you can try to approximate the model. We discussed this. You can try to approximate the optimal action value function. You can try to say that I'm only dealing with MVPs where all the action value functions are well approximated. There are all of these cases. If there are no approximation errors, then we have very little reason to believe that this wouldn't hold, and the algorithms that we have seen before for the positive case wouldn't go through. Indeed, lo and behold, nothing much changes. But if there are approximation errors, there are funky things that are happening. So we have already discussed this a little bit in one of the lecture notes, that if there are function approximation errors, then there is an information theoretical bottleneck, whereas you can't really compete with policies which are epsilon optimal if you have, or you can't really expect to, not even that, you can't really even expect the approximation error of a sample efficient algorithm to scale with the best possible function approximation error unless you allow a blow-up factor of square root of d, right? Like, so this was the lower bound construction based on the Johnson-Linden-Strauss lemma. It shows that there are some feature maps that is blow-up is such that you just need, if you want to compete with the epsilon error, then you need exponential in the dimension samples, which is not what we want in general. And that was set up for the friendlier planning case where you can control where you are sampling. So in the batch setting, you can't even control where you're sampling. So it can't really get much better than this, right? So that's kind of the starting point. There's still interesting questions as to, like, okay, can we even get this? If we are only talking about, something like bandits, contextual bandits, there is no dynamics. The least squares is getting the square root d error. In the case when you have an optimal design. Of course, if you don't have optimal design, you may or may not get it, right? So that is somehow this is the question that is the interesting question when it comes to batch reinforcement learning and function approximation. So it's basically, how should we estimate value functions of policies? So estimating value functions of policies is, of course, a special case of estimating the value function of the optimal policy. So that can only be harder. So if you would find it hard to estimate the action value function of a policy, then you can expect that, okay, estimating the optimal action value function will only be harder. So that is the first question. So you have a bunch of samples, and what are those? So it's a function approximation case. So you have a bunch of samples, as usual. So these are these triplets or quadruplets, actually. Where Si prime follows transition distribution, and the expectation of R of I is correct. This holds for every I. And the simplest case would be this is I at D. The other case is when this is trajectory is cut up into this quadruples. And then you have some correlations between them. So there is this sample, but the real case is when you don't see the sample, you have features that map the state action pair to RD, and you have a stochastic policy. It's a memoryless policy with the state space and action space, maybe it's stochastic, maybe it's not. So the NDP itself induces a value function for this. And the data that you see, this is the data, it's phi of, okay, right, okay, let me change a little bit the setting to simplify it. So we're going to estimate state value functions, okay? We're not estimating action value functions. So the features are going to extract features of state. We can then discuss what happens in the other case. In this case, this is what happens. Sorry. The data that you see is this. All right? This is the data that you see. And from this, you need to estimate V pi. So you need some map, some algorithm, whatnot. Is there any question here? There was
We
something.
don't hear anything.
Oh man. Okay, I was muted. You're the boss.
No, it's not problem.
You can mute me or unmute me, but I'm not sure about unmute. Anyways, thanks for pinging. Okay.
Now it's perfect.
I don't know what happened. Because at the beginning you could hear me, right?
Yeah, yeah. Beginning we were able to hear, but suddenly, like, you were muted.
Okay. Anyway, fixed. How much did you miss? The whole
After the
thing?
question.
Huh?
After the question. So someone asked question regarding some features. I was not able to get the question properly.
Did anyone ask a question about features?
Someone was asking some question, I think. Or maybe, like, at that point, yeah, I was confused because I couldn't hear anything.
Right. Okay, anyways. But is this clear? It's like the setup is clear. You only see this data. From the data, you want to estimate a value function.
Right.
Okay, so one of the things is that when we say we want to estimate a value function, what do we really mean? We can mean many things. So one of the things, at least two different things. One of the things is that we want to construct a function, I don't know, call it f, that maps states to reals, such that this function is in some norm a good approximation to the value function. The value function is a map from states to reals. This is one of the possibilities. Is this really what we want? Many times when we are in this feature scenario, we are in this feature scenario because we don't actually see the state. We only see the features of the state. If we only see the features of the state, then it's not useful, and it's like not even like you can come up with a function that maps states to something, but you will not be able to use it because you only see the features of the states. So option number 2 is to come up with some function that maps the feature space to reals, such that if you're composing this function with the feature map, so feature map maps from states to RD, this function maps from RD to reals, you compose them, you get a map from states to reals, and then you can compare with the value function. And so you may ask for this. So which function g is going to make this small? from this perspective, that the features are mapping to RD or some absolutely arbitrary other set. Doesn't matter. Could be any other set from option number 2, from that point of view, right? We're not using the vector space structure of RD at this stage. So option number 3 uses this structure. So here we are asking for something like a vector in RD such that if you take the inner product of the feature at some state with theta, creates this map that goes from states to reals, and this should be closed as a map to the value function. So that's option number 3. So I say option number 1 is out. I don't think that that's a too interesting question because, like, what would you use it for? You can't really use that. So option number 2 is a little bit more interesting because you see the features. No one ever forces you to, even though if the features are, no one really ever forces you to use a linear map. You could use piecewise linear, you could do whatever, right? Like, you chop up the space into different parts, this RD, and different parts, different coefficients. You can create a complicated map if you want. So that's, I think, interesting. And option number 3 is, of course, interesting because that's the simplest possibility. And we may be interested in, like, okay, like, how well can we do if we demand that? So this is all good. The question is, the next question maybe, is what norm to use? And the other question is, what do we mean by small? Like, how small is small? So for the norm, I'm going to propose to use the infinity norm. So it doesn't matter what you use here, because we're not talking about that case. And we have seen that pretty much all the proofs just use the infinity norm anyways, because it's such a nice complementary norm to the structure of MDPs, because they bring in an L1 norm because of the distributions, and the dual of the L1 norm is the L infinity norm. That's why the L infinity norm it happens to be a very natural choice. It's a dual norm to the L1 norm. And if we can control the L infinity norm, then we can control pretty much everything. If we can only control some other norm, not L infinity, but some weighted P norm, for example, then very often it is very hard to get any further results in terms of the bigger algorithmic questions of, like, how good my algorithm is approximating a policy and so on and so forth. It's not impossible. In fact, you can, for example, if you run the polytech analysis, you see that L1 norms pop up. That's kind of the weakest norm. But that with respect to measures which are not under your control. So for example, L1 weighted with respect to the distribution induced by the optimal policy. And that's not a measure you are controlling, and that's not a measure that your samples are typically going to correspond to, because if you could do that, you would have already solved the problem, because you're sampling from the optimal policy, then, like, what's going on? Like, although this is not really a choice that is unquestionably the correct choice, the infinity norms. clearly it is a choice such that if you can control that, then all will be fine. So it's the first question to ask. Okay, so the next question is, so what are our expectations? Like how good things should be? Well, the features may be imperfect, right? So maybe there is an ultimate error with which you can approximate things. So here, it's pretty obvious you could just choose the best possible map, G, that you can, if you're composing the map with phi, then it gives you the smallest error. So this is the ideal G. So the ideal G is given by this infimum. And first maybe we will need to think about like what would be this ideal G? How does it look like? What would it do? Okay? So that will be question number 1. Question number 2. I mean, okay, so here there is the corresponding metric that if you can only use linear functions, so therefore you can only choose a parameter vector, then this error, of course, is going to be generally larger than the error when you have no restrictions on what form G takes. So that's very clear. And so the questions, so the question number 1 would be like, how does G look like, the optimal G? Then here you could ask like, what is the optimum theta? Well, the optimum theta just solves this. So it's like, I think that's, you can just say that, okay, there is this minimization problem, but here you can kind of see what the solution to the minimization problem is. Here the solution to the minimization problem is just like a wide convex optimization problem. Like you can't really say much cleverness about that. So that's not too interesting. What's more interesting is that if you have data, can you come close to this optimum, or can you come close to this optimum, and to what degree? And relative to these errors, how well can you do? And so one corner, one extreme case of this question is when you have infinitely many data points. If you have infinitely many data points, you don't care about computational cost or anything, then we're just caring about the information structure of the problem. So by infinitely many data, what do we mean? Like if you have infinitely many data from a distribution, you apparently know the distribution, right? That's equivalent to saying that you know the distribution. So this data, like a quadruplet here, has some distribution. Call it Q. So this is a distribution over RD cross action set cross reals cross RD. So someone gives you this distribution, and from this distribution, can you reconstruct G star? If you can't reconstruct G star, can you reconstruct something that is like, almost as good as G star? And how would you do that? How would that construction look like? The same question here. right? So at least we should be able to answer the limiting question. Of course, at the end, we're going to have finite data, and we'll need to go back and ask the question, what can we do if we have finite amount of data, and answer the same questions. Okay, so let's start with G star. So what is G star? Can you think about some function there which would be optimal?
The inverse of u applied to v pi?
There is no u.
G
There is g and phi and v pi.
of, oh, phi.
Which one? Phi? Oh yeah. So this is not u.
Yeah, now I see.
This would be my u.
Yes, yes.
Okay. The inverse of phi.
Phi.
So the inverse of phi. Okay. So how does it look like? Here is S. This goes to RD. You take a point. So this was phi. If you take a point here, call it x. This is phi inverse x. All these states are mapped to x.
Oh,
Okay.
okay, so no.
So what do we do with that? So we can take this inverse map. I go with what you said, like the inverse map. I think it's a good idea. The inverse map, if you're taking two different axes here, what do we get? Different sets. If we take all possible axes, what do we get here? It's gonna be, huh?
All set?
All what?
All the sets? Like all the sets could be.
Right, it's called a partition, right? Like we get a set system such that the sets in the set system are disjoint, but they need to cover the whole space. Okay? So this phi of x, where x is in RD, for this is an empty set if this is not in the range. So that you throw the empty set. This is a partition. Okay, so this is set system. It's a partitioning of S. In other words, you can imagine, here is your S. What phi does is that it pulls together a bunch of states, maps them to the same vector. That's all what it does. Creates a partition. So all these states are mapped to the same vector. So now, if we just focus on one part of the partition, zoom it out. So the V function itself, I don't know, like I can't draw it. Okay, so this partition is actually one-dimensional, and here is your V function over it. This is V pi, and this is just one part. So this partition is just like thrown as a line. Okay. What do? We need to approximate this function. We are forced to use the same value because G doesn't see the states, it only sees the vectors, the feature vectors of the states. So for G and this function approximators there, all these states are mapped to the same value. So it can only, or a predictor of the value can only assign a single value to all these states. This is how this function looks like across all these states. And we want to keep the first error to be the smallest across the whole state space, but that also means that we want to keep the worst error over a part also the smallest. So here, in this part, we can only use a constant Where should I put the constant? Should I put it here?
Between the range, like the middle point of the range.
Oh, okay. So, yeah, like this would be a horrible choice because this is a big error. This would be even worse, like if I go below, then yeah, it's an even bigger error. If I go, at a maximum, okay, this is the largest error then. That's not good. So which value is going to give me the smallest error, smallest worst case error? Mean plus max over 2. It's the middle of the range. Right? So this is the mean. This is the max. Take the mean plus max over 2. The error itself in this partition is going to be the size of the range divided by 2. And this is the best possible choice. So now we understand how G star looks like. It's going to be piecewise constant. It has to be if we view the composition of G and phi is going to be piecewise constant over S, over these partitions, and in any of these partitions, the error is going to be half of the range of the variability of the function that we are approximating. Right? So that's how it looks like. That's G star. Next question. If we now need to construct an estimate, so this was using detailed knowledge of V pi. It's like we looked at all possible values of V pi across this partition, and is that information going to be available if you only see Q, this distribution here? Okay, so the simplest setting, okay, let's replace this Q by just like, not worry about the next state. We're just doing, and there is no action. We're just doing regression. So these are values, okay, so this is really the value. So just worry about that case first. Simple case. It's like a bandit problem. Gamma equals 0. Because then the next states don't matter. And let's forget about actions. That's like a minor variation of with the actions. It's not important. So now we only have feature vector. So that's like which partition you are. And for each partition, there's a distribution over the values. It's going to depend on what's the sampling distribution. So there is this underlying sampling distribution over the state space. If you restrict it to this partition, it has a sampling distribution over this partition. And then you see all these values popping up according to the sampling distribution. That's what you see. That's the data that you see. So it's basically for every partition, you see a distribution over areas. So not this detailed function, not the minimum and the maximum, but a distribution. But and the distribution, if you have noise with the values, it might not give you this range. If you're seeing these values without noise, then you get exactly this range. But no, we're gonna have noise. Proper reward noise, proper value noise, whatnot, then basically you have a distribution like this. Well, it was an arbitrary, maybe you won't have a distribution like this, but you will have something like this. It can go over the range. If we didn't go over the range, we would just like, oh, yeah, we can take the max and the mean, divide by 2, we get an optimum. But if you have noise, that's not an option. What can you do? For every partition, you see a distribution over the years. What value are you going to use? let's use the expected value. So that's, I mean, that's something that one would try, right? So we can take, so let's still call this R, still R, but gamma equals 0. So the value function is really just immediate reward. So we can take the expected value of the reward given that the feature vector equals some x. So we had this part, this distribution. Where's the mean? Oh, okay, it happens to be almost the same as the mode, but not quite. This is the mode.
Is the expected value the best statistical value?
We just made it up. No one said it. That is the best. What other choice would you have? What other choice you want to have? So from the distribution, you can get any real value. You could take, what would be another choice?
The mode would be one.
The mode, right? So can we draw an example where the mode is a horrible choice? I don't know. Maybe it's not a horrible choice.
I believe both the expectation and the mode can be very bad choices.
How bad?
For arbitrary distribution.
How bad? That will be the next question, right?
Yeah.
So now, is it really bad? So expected value would be one choice, maybe the mode.
Are we not assuming finite support of the distribution, right?
We're not making much assumptions. If you would, how would that help? I mean, like, I can put a lot of points here, everywhere. So it has a finite support, but it's all over the place, and it's kind of approximating any, other distribution with finite support distribution. So I don't think that the finite support would necessarily help.
Just one thing, when you said we had noise, does it mean like the rewards are noisy?
Yeah.
And
It's like you had Gaussian noise on the top of immediate reward.
Okay, and then our target is the expected value.
Yeah.
Those things, okay.
Right. Yeah. Right. Exactly. So this is this condition here.
How about calculate the window of some quantile? For example, 25% quantile and 7.5% quantile.
Yeah.
Maybe some.
Yeah.
Some, yeah.
Maybe.
Because there's no knowledge about the noise, we cannot really say anything about it, I guess.
Okay. So there is a question of the mode of, I have this general notation that if you have random variables, you just write a P, and then you can write R and X, and this creates the condition distribution, okay? Of the reward given the feature vector that you're observing. You could talk about, I don't know, the average of the quantile of this at, I don't know, 1/4 plus the same thing at 3/4, and so on and so forth. My instinct is to go with the expected value. Can you explain why I have my instinct? Yeah.
I mean, because those targets are existed. If, for example, those partitions where like each one has one state, then and
I think it has nothing to do with the partitions.
I mean, if you had like each partition has one state, and we have like our target was our data set size was big enough, then it
Oh, this would be perfect.
yes.
That's what you said. It's like, at least in the case, oh yeah, that's pretty good. At least in the case when the feature vector is not losing information, we won't get back the perfect answer. It's somewhat made up, but like it's a good property to have.
Like, based on my intuition, like using this expected value for a very skewed, I guess, distribution would be very bad, like compared to something like the minimum plus maximum of the same thing, because, like, you know, because we are trying to minimize the maximum norm, so for a very skewed distribution, the expected value would be very far from the other end of the distribution. So this will result in a very high.
Interesting. I see that you're going to argue the opposite. Because your argument seems to be perfect to argue against anything but the expected value.
Like,
Because we want the expected value, the immediate reward is defined using expected value. So the only thing that we know at this stage about the noise, that it has zero mean. We have no idea about how the tail behaves. The quantile is really about the tail behavior of the noise. And the only thing we know is that we want to recheck the noise, I mean filter it out, like average it out.
but what if the reward is deterministic? Like for that case.
But we don't know. We don't know whether the reward is deterministic or not. We just see this noisy reward. And we want something that works always. I know where you're going, like you want some robustness, blah, blah, blah. But it's kind of funny because this is not how to get robustness here. Because at this point, we already kind of like set our minds on that we have noise, which is zero mean. We need to reject or filter out the noise. Therefore, that implies that we need to take expectations. Yeah. So, we go with the expectations.
Back to the previous point, if the distribution is bounded, maybe you can bound easily how bad your choice of expectation can be.
Huh?
If the distribution has finite supports, or
Yeah.
you can bound easily how bad your choice would be.
There could be very, very far away points in this. I mean, again, finite support doesn't seem to matter to me. Yeah. It's like just generally the noise can enlarge this range, and some of the only way to remove that and be faithful to the assumption that the only thing that you know about the reward is the expectation is correct, is to use the expected value. Because that actually centers the reward pointwise. And somehow what happens here is that there are two integrations. For every state, we have the reward noise. We are integrating the route first. Now we get the correct value. And then, so this is this function here. The expected value operator is doing this for us for free. And now we have kind of not this function, but a distribution of these values in a way. And so at least this average is certainly in this range. Because if this is in this range, the approximation error that you're going to get is at most double of the best error, which was to choose the midpoint. If we are unlucky, we can be here, in which case we double the approximation error. That's all. All right? So this is not a bad choice. So G, I don't know. I would call this a base function. So the approximation error of this is at most 2 times. So 2, that's good. That's happy. But this function can be very complex, right? It's like how many different values you can observe and so on and so forth. Very, very complex. Storing, whatnot. So ultimately we want this parameter vector. the linear stuff. Question, what do we do? So we have this distribution Q, and now we want to use this distribution to come up with a vector theta. So this theta here is based on, again, the detailed knowledge of V. It's like this detail within a partition, it's not given to us. We see a blur over there. It's just like you have this collection of conditional distributions over the rewards. And now you need to use somehow the linear structure. So what can we do? Huh?
Optimization. Some sort of optimization. We probably won't have closed form solution.
Sure. What optimization problem should we be solving? I mean, like, this is not closed formula A either, right? Like,
Partition's gone.
yeah. But now the partitions are gone, so you need to kind of have a unified answer. Through some simple ideas. Okay. Here. Okay. Click. Oh.
Sorry, you're muted again somehow. I don't know how.
All right. Okay. I see that you want to make a suggestion.
No, because yeah, you were muted. I didn't.
Okay. There was a question of, okay, throw at me some ideas about what would you use if you need to come up with this parameter vector, and you only see this joint distribution. Tell me something.
It's like least squares policy, like the evaluation step of like LSPI would do this, would minimize this.
So we could try least squares regression,
Yes.
right? Basically, regress of the reward, because now we only have rewards. It's kind of bad in problem. So yeah, that's one choice.
They just have to deal without finite data somehow. Like with how, I mean, like compared to the planning case, we now have this finite batch of data we have to adapt. Like, I mean, we had this in planning that we could like roll out things, and we have now this batch.
We actually have infinite amount of data, so you can write integrals and whatnot. So we just write the ideal integral that least squares would converge to in the limit of infinite amount of data. So what's that? It's like, this is the feature vector, and we need to correlate it with the data that we have. But least squares sneakily takes expectations there in this spot. Yes, so that is being filtered out. Okay, so there is, so in Q, this distribution is the product of mu, and this other distribution is marginal of R given X. Okay? So here we need to integrate according to mu, and G is also just this integral with respect to mu of the order products of the feature vectors is I matrix. The limit of infinite amount of data. Okay, so this is one possibility, and we have to we need to wish that this is invertible. What happens if G is not invertible? We drop a dimension or two, or more, as many as we need. Pseudo-inverse. Least squares, yes. That's fine. Wait. Huh. I can only, no. Okay, so this was, okay. Oh, what am I doing? It's, wow. Yeah, V pi is defined over S. So I can't do that. So, that is a distribution over the states. Call it mu S. And if you push it forward according to phi, you get this mu, the induced distribution over the features. So here, I need to use the states. No, can't use the states. Can only use phi S.
V pi was in S.
So then it's all fine. Like everything was fine. Okay. Okay. Let me clarify. So, yeah, this is the right. This is the correlation of the wave function with the features according to the sampling distribution. But if you push it forward, then this is the same as if you just write everything in terms of the features. So the mu is defined exactly such that this equal is equal. Yes.
Isn't V pi defined on the states themselves?
V pi is defined on the V pi is defined on the states. That's why. Okay, that's why I'm writing this. Okay, yeah. Sure. Yeah. Okay, that's fine. Okay. See, it's like, oh, thank you. Right. And okay, so I can note now that this is the same as this other one. So the data. Let's see. So this would be just like running least squares.
It should be x multiplied by h transpose instead of phi x multiplied phi h transpose. Last line.
Yeah, absolutely. Okay. Okay. So whenever we see something like this G inverse business. And whenever we see G inverse, we need to worry about blowing up errors. Like I already noted that this could be singular. What's even worse is that it can have a very small minimum eigenvalue. And there's a small minimum eigenvalue that's like, in a way, even worse. So somehow the smallest minimum eigenvalue tends to appear in all the error bonds. So here we have this minimum error, epsilon star ln. And how much are we going to blow this up if we run this least squares? So the only way argue about these things is to compare. So that is theta star, the ideal parameter vector. So if you want to control the L infinity error between two linear functions, then this essentially boils down, I can't do better, than to say that the two parameter vectors are close to each other. If they're close to each other, so if let's do it. So okay, I don't have to write a phi. I can write x. I think. I have to write it. So I want to control this error. And I'm content if this error is comparable to epsilon star ln. So I want to bring in theta star. So we know that phi transpose theta star is a good approximation to V pi in the sense that like we can ignore errors of that size. So bring in phi transpose theta star, subtract and add, use triangle inequality. So here we get an error which is this equals to the optimum error. So we need to somehow argue about this. And so here there is a maximum over all possible feature vectors. So that's like a norm, right? So the max where x is in phi of s, and that better be compact, x transpose theta ls minus, this is just absolute value, sorry, absolute value, and theta star. So this is the definition of almost a norm with respect to this set. So if this set would be a unit ball, for example, but it's included in the unit ball, the other unit ball, for example, then you basically get a scaling of the two norm here. So you can't do much better here than to maybe upper bound this using Cauchy-Schwarz with the max over phi s of the norm of x and the Dua norm of theta ls minus theta star. And so if you choose an arbitrary norm, that is the Dua norm of it. And if this happens to be the 2 norm, let's just choose the 2 norm for simplicity, and this is also the 2 norm. Or you could choose here, maybe you could choose G inverse. Maybe that's a little bit better. This is G. Okay, anyways. Before we go there, just wanted to say, okay, you can choose these norms. Maybe you choose the 2 norm. That's a simple choice. Because maybe the only thing that you know is that this is upper bounded by a constant, like B. Okay? Then you still need to control this 2 norm. And so here, we had this previous calculation. So basically, you write this as epsilon s plus theta star transpose phi s. And you will have two terms, this term and this term. This is the approximation errors. And if you're subtracting these two guys from each other, you will see that only these terms remain. And you need to control them, and we were doing the control, and you saw that it's basically the minimum eigenvalue of G minus 1/2 is that's going to show up of the maximum errors of the epsilon. So we were doing this calculation before. So this is maybe not the best. So maybe there is a better choice. So what would be a better choice than the least squares estimator if we know this distribution? So don't think procedurally, think about like what is the information that you have. Yes?
I just have a question, like, what's the difference between having an infinite amount of data and having a simulator? Because it's kind of like...
Having a simulator.
Yeah, because we already have infinite samples for each of the state action pairs we want. So...
Not each of the state action pairs that we want. We don't have access to the states. We can't control the distribution over the states. So in a simulator access, maybe we would be able to do that. So here we can't. So that's like batch. Yeah, I think that's the main difference. Otherwise, yeah, they're very similar, especially infinite amount of data. It's more like knowing the distributions, but it's like just knowing the distributions after you move into this space where a lot of states are collapsed. So a lot of things are merged together. Okay. Oh, there was a text. Oh, I think that it was Slack. Slack makes this noise. Okay.
We have to somehow reject V pi on the span of phi in this infinity norm. That you do to us.
Can we connect maybe to this? So what is the problem? Why can't we use theta star? Because we don't have access to V pi. Otherwise, we would just use theta star. Why can't we use it? We don't have access to V pi. But we do have access to what? Infinite amount of data gives us access to G star. So how about replacing this with a composition of G star and phi, get the minimizer, so call it, I don't know, theta hat star. This doesn't have any least squares business, minimum eigenvalue, nothing. It was just going, doing the partitioning, the best approximation with respect to the partitioning, and then the best linear approximation to that. And you can write a bunch of triangle inequalities, and you will see again that this error is going to be multiplied by at most, I don't know, 3. Maybe it's 2. I can only prove 3, but I'm not going to do it. It's not hard. It's just a bunch of triangle inequalities. Maybe someone can save a few triangle inequalities, and it will be 2. Oh, with respect to this, the previous 2 that we got, from the figure you kind of see that the 2 is the best possible. You can't do much better than 2. You can't do better than 2. You can prove that. No, it's not possible to get a better than factor of 2 approximation. Here, similarly, you can prove a lower probability 2, but not a 3. I don't know. So big open question. Maybe not so big. And okay, so I think so here to give this just, I think that if you are more clever with the norms here, then maybe you can put the chi inverse here, the chi there. You still suffer this, so it's kind of like almost the same as the minimum eigenvalue, but it's like, okay, if in the direction of the features things are not so bad, then it could be a little bit better. It's like a restricted minimum eigenvalue condition. Okay. So this was all bandits. So no for reinforcement learning, doing finally with data like this. So there are analogous ideas. So the analog to this idea of coming up with G star, the base estimator, is to estimate the transition model over the partitions using base rule, estimate the rewards over the partitions. It's like aggregation. Question? Oh, we were muted. Okay. So this is estimating a model over the partitions. If you estimate the model over the partitions, and you were promised that the value function can be approximated up to an epsilon accuracy, you're, let's say, in a discounted setting, how well can you approximate the value function? What's the approximation factor? And the discount factor was 0, it was 2. If you have a discount factor, what do you think what it is going to be?
2 over 1 minus gamma.
Yeah, it's like probably 2 over 1 minus gamma. You have to pay for that horizon, so you do. You can prove that that's unimprovable. So now, can we repeat this procedure where replacing V pi with the idealized model based and then get the best linear approximation? Yes, that also works. It gives you a factor of 2 or like 3 over 1 minus gamma or something. And this is still not too satisfactory. We are using an infinite amount of data. It's satisfactory in terms of that, okay, the approximation error is only blown up by so much. A procedure, what would be a procedure that kind of like does what the least squares do, just for reinforcement learning?
Policy evaluation.
Yeah, it's like least squares policy evaluations, LSTD or whatnot. There comes interesting things. So if you have LSTD, and you have no restriction on the sampling distribution on the states, then there is an example that shows that the approximation error is going to be blown up infinitely by an infinite amount. So the approximation error, like you can design a sequence of problems such that the approximation error converges to 0, and like somehow the approximation error for LSTD just stays constant, just returns the same answer always. So that's like
We did this?
really interesting. This is Zico Kotter
Oh, okay.
a while ago. And this is because there is, I mean, okay, one way of getting rid of this and get at least to somewhere that least squares can get us. Actually, least squares, if you push it hard, can get you the square root D approximation. So even for this offline case. And if, or minimum eigen, okay, anyways, at least the minimum eigenvalue can show up of G. And if that is controlled, then it's all fine. If it's not controlled, then it's like, okay, it's too bad. Yes?
Has anyone been able to introduce a regularizer to kind of balance lambda min and epsilon infinity? Like you introduce some like lambda such that, you know, you balance these two terms. So that like, because if you introduce lambda equals, for instance, infinity.
So I started to say that there is an impossibility result that says that you can't do this. So you will have an exponential compute cost or an exponential sample cost. It doesn't matter, like either of the two. You have to pay.
If you introduce a regularizer?
No.
Oh,
regardless of like,
okay.
if you want to compete up to constant factor is the best approximation error, then there is an exponential cost in the dimension to that.
Okay.
And yeah, if the exponential cost doesn't bother someone, then yes, you can design procedures. All right, so, but value function approximation is a little bit worse than that, because in the uncontrolled case, it's not even a minimum eigenvalue. We don't actually know what to do there to get anything like with the minimum eigenvalue. Okay, so there is a real disconnect. If we are in the own policy case, that means that you're running a Markov chain and you're generating the states from the stationary distribution of that Markov chain. Then there is a very helpful weighted two-norm contraction that happens. And that has been used to argue that in this weighted two-norm, you can approximate well the value function. But essentially, if you can approximate well in this weighted two-norm, that also means that the parameter vector can be well approximated. And that also means that the maximum error can also be kept small. You just bring in the minimum eigenvalue and you're done. So we see that in the off-policy case, we don't really know what to do. What is a good procedure which would be as good as if you didn't have, as if you had gamma equals 0, then like you have some results. For gamma positive, we don't know. Yeah, I think that this is all.
So this procedure bit was because of, like, I just didn't get it. Like, why is it that we don't have a good procedure in this case?
It's just like, because the obvious ideas don't work.
Oh, I mean, like rolling out.
There is no rolling out. You just know this distribution, and from this distribution you need to get something. And with a computational efficient way, and you are willing to pay the minimum eigenvalue cost, but not more. That is the problem. Yeah, so maybe it is not possible to do it. We only know that LSTD will not do it, but we don't know whether there is some other design that would be able to do that. So Zico's example is just specific to LSTD. He just says, no, LSTD is not going to cut So I think that's a very nice problem. All right, so we see that already basic stuff like approximating value functions is a lot of fun, and it's we are just scratching the surface here. We started with state value functions. It's a little bit more complicated if you have state action value functions, because then you have to say like what is the data that you have there. If you start to have trajectories, then it's like, okay, what is the next state next action distribution? And I don't know, like it gets a little bit more complicated in terms of writing. I'm not sure whether the lessons would be very different. I suppose they're pretty similar, but no one has done it. By the way, this is none of this is in the literature, and this came out from the visit of Phil on Montilla. Last summer, some of you may have met him and Nanjiang, who was not visiting, but he's also had been thinking about this, and he has some notes that were independently developed.
Has he solved this yet?
Then I would tell you if he solved it, right?
Just remember, I know he really wants to solve it, that's why I wasn't sure. I know he really wants to solve it, that's why I wasn't sure if he's close.
No, I guess we will get it, but we haven't quite finished it. I'm like, what you have seen today, we got this far. Took us a while. All right, questions? Oh, just one last note.